Welcome to this HVDC transmission video course in NPTEL program phase 2. The first lecture I will be discussing about this evolution of HVDC transmission system. First I will discuss what are the various contents in the various modules, and then I will discuss about the first module and contents 1, that is the evolution of HVDC system. So this HVDC transmission system course is divided in 7 modules, and the first module basically it is including the evolution of HVDC transmission system, and then in this evolution of HVDC system, before that I will discuss about the evolution of power system. Then we will see how this HVDC came into the picture along with the AC transmission system. Then I will compare the HVAC and HVDC systems together, and we will see the various problems in HVAC system and then HVDC systems, and also their advantages and the disadvantages in the system. Then I will discuss about the various type of HVDC transmission systems, that is the various links, and then in that module the last lecture, this lecture number 4, will be dedicated to the components of HVDC transmission system, including your converter, DC lines, your converter transformers, and other filters and smoothing reactor, etc. In module 2, it will be devoted to the analysis of the converter circuit, and you know the converter is very important in HVDC transmission system. That is, we are having rectifier side as well as the inverter operations as the inverter end. So these converters are very important in HVDC transmission. So module 2 is completely dedicated for the analysis of the converter circuit, and this HVDC converter circuit will be represented by the equivalent electrical circuit at the end. To start with, first I will discuss in this module, that is analysis of the simple rectifier circuit. It may be the single phase rectifier circuit, and also along with we will see the 3-phase circuits. Then we will go for the various configurations, and we will see what are the advantages and the disadvantages. We will see the various terminologies, those will be used, like the DC output voltage, peak inverse voltages, and commutation group as well. Then with this terminology I will jump to the required feature for the rectification operation or rectifier circuit operation in HVDC link. So we will see the various requirements, that we require the high output DC voltage for a given input AC voltage. We require the better transformer utilization. We will also see the less peak inverse voltage. Also we will be requiring that the harmonics should be minimum. So these are the basically desired features, and based on that we will arrive the what should be the optimal configuration for this HVDC converters. After deciding the converter circuits, that is the 6-pulse converter circuit will be analyzed for the different modes of the operation. Different modes, I mean basically the overlap angle I will be discussing. Overlap angle means the one valve or one thyristor is taking current, and then it is another is going to be turned on. Then how the current is going to shift it. It is instantaneous, that is ideal case. Then we will say the value of U, that is overlap, the current shifting from one valve to another valve. The value is the U angle. If it is less than 60, then it is mode 1. If it is 60, then it is mode 2. If it is more than 60, then mode 3 and 4 operations we will see. So based on that, the output voltage as well as the waveform will change, and then we will analyze detail about this circuit. So in both output waveforms of various modes, we will analyze both waveforms, like the valve voltage, the DC output voltage, currents in the phases of the transformer, and also we will see this what will be the DC average value of the rectification operation, and similarly we will see for the inverter operation as well. Now we will also, as here already I have mentioned, thus we are also going to discuss the valve voltages. This is very important, because if the voltage of valve should be known, then we can see what are the various mal operations of the valve, and based on that we will design some circuit to avoid the mal operations of the valve. After this, once we are having the complete analysis, we can form, means we can substitute this HVDC link by simple equivalent electrical circuit having a variable voltage source and with some commutation resistances and the line resistances, and then we can calculate the current in the DC link. Another part of this module 2 is basically analysis is based on the converter charts. We will see the converter charts, basically the DC variables. We are having alpha, delta, and gamma and the beta are the DC variables. So we are going to draw on the two planes. One is the DC voltage and DC current, then we will see the DC variables impact and the current converter chart will be drawn. And another one will see the AC variables like P and Q will be your axes, and then we will see your power factor, apparent power, AC current, etc. will be, and reactive power as well, and in another chart. So, this two variety of charts will be discussed, and then we will see based on that how that we can analyze for any particular current we can get the voltage U and other angles as well. So, third module basically now is dedicated for the converter control. In the first lecture, I will be discussing about this what are the desired features of HVDC control, and then we will go for the various control modes. We will derive the control characteristic that should be the suitable for the HVDC transmission operation, and then we will discuss the various type of control schemes for the firing of the valves, because in HVDC this is the main what we are doing, we are generating the gate pulses to turn on your valves or thyristors, and then we will see the various comparisons of various schemes suggested by various inventors, and we will see which are the bad and which are the myths. We can say we are going for the demerits and the merits of the various control schemes. Another lecture will be dedicated for the energization and the de-energization of bridges. If your HVDC link is having the many more than two bridges in converter side or inverter side, and if you want to take one bridge out of operation for the maintenance and other purposes, then how you are going to de-energize, how you are going to bypass that bridge, and again once it is repaired, then how you are going to put into the HVDC link again. So, energization and de-energization are discussed in detail in this module 3 as well. Another aspect of here, even though if suppose your HVDC link is down for some maintenance or some problem in the fault in the DC line, then we have to start the HVDC line, then how to start it. So, the starting concept will be discussed, and also if you want to take whole HVDC link down for any maintenance, another repair or any other purposes, then what should be the stopping way procedures is basically discussed in your starting and stopping of HVDC link. In module 4, basically it is dedicated for the protection as well as the mal-operation of the converter circuit. So, the converter circuit mal-operations, the various mal-operations in the converter circuits are discussed, including your arc back, arc through, misfire, commutation failure, quenching, all will be discussed in detail along with the wave shapes of your output voltage as well as the valve voltages. And but the commutation failure, which is only occurring in your inverter side, it is a very frequent phenomena. It is discussed again in detail for the single commutation failure, or it is a double commutation failure. Single commutation failure means in one cycle it is only one commutation failure. If it is happening more than one, so it is called multiple commutation failure. So, in this module the first and second commutation failures are discussed, and we will see what will be the output voltages, what will be the impact of the valve voltages, etc. will be analyzed. Then we will see how to protect overall converter circuit. That is, we want to protect the converter circuit, we want to protect our HVDC lines. So, we are going for the over voltage protection, we are going for the over current protections similar to your AC current, and also we are going to have the differential protections for the checking the link differential current. So, the complete inverter as well as your rectifier side system protection is discussed. Another discuss here this smoothing reactors, basically the DC reactor I am discussing, and this DC reactor is, if it is used to limit the rate of rise of voltage or current, so what will be the inductance values. So, this is basically is discussed, and one problem is also solved. Then in this module as well the damper circuit, because we are having the various type of dampers like the voltage oscillations if they are there, then we are going to have the anode dampers, if you are going to have the current oscillations, if you are going to have a line oscillation. So, we are having the various RC and RLC dampers are used, and they are discussed in detail in this module. Module 5 is basically dedicated to design the various aspects, because we have to design the filter circuit, we have to design the grounding and the DC lines. So, to design the filters, we have to analyze the whole converter's operation and its So, we want to know what are the various type of harmonics. So, various harmonics, that is the characteristic and uncharacteristic harmonics, are discussed and analyzed for the 6 pulse operation as well as the 12 pulse operation of the HVDC link, and based on that we are going to design the filter circuit. So, we will see the various options for the, that is a tuned filter circuit, or it is a your bypass band pass filter circuits design. So, the design of the filter will be done in this lecture. Another aspect of this module, that it will be also analyze the reactive power requirements, and we will analyze even the filter circuit if it is designed for particular harmonics to provide the minimum impedance for that harmonics, but this filter circuit provides the reactive power support to the converters for the fundamental components, and that will be analyzed, and we will see the requirement of your reactive power. So, in your module 6 is completely dedicated for the power system analysis aspect. So, here first I will model the various components of AC/DC systems, including your DC, the base powers, etc. For AC and DC completely, we have to match the AC base powers and the voltage, and also the DC base power as well as the voltage, and then we will model them in detail, and later then we will go for the AC/DC load flow. Various techniques are already suggested, that is a sequential based AC/DC power flow analysis, or it is elimination based or unified schemes. They are discussed much in detail in this module 6. After the modeling, this module is also will be discussing here the various stability analysis, like the transient stability analysis, as well as we will also discuss our the dynamic stability analysis in this module. The last module, that is module 7, is basically dedicated for the diverse aspect, like new concept is arising. This HVDC light is basically using the transistor technology. It is very fast, as well as the communication requirement is reduced. It has various advantages, so that will be discussed. Also, we will discuss about the multi-terminal HVDC link, because till now up to the module 5th, I discussed about only the 2-terminal HVDC. So, in this 7 we will discuss the aspects, problems, and what are the advantages of multi-terminal HVDC links. Then the last lecture will be dedicated for this HVDC system that is used for the wind power generations. In the wind farm generations, you know, the wind farms may be located very far from the actual load centers. It may be even though in off source, so it may be sea. So, we have to see how this HVDC system is useful and beneficial for the wind power and the green power generation in whole power system. So, these are the brief course contents of this HVDC transmission system video course, that is NPTEL phase 2. Now, as in the first part of this lecture, I will be discussing the evolution of the power system. Then we will move that and we will see how the HVDC system came. So, to start with, you can see this slide here. The commercial use of electricity basically started in late 1870s, but the first power system was developed by your Thomas Alva Edison. It was at Pearl Street of Newark Station, and it was commissioned and operated in 1882. This was the DC system. It is surprising, but it was the low voltage DC system. But however, this course is devoted for the high voltage system. So, that time the high voltage DC system was not possible, because there were several problems, like your generations, because it was the DC generators it was used, and also to transmit the power, the insulation and other problems were there. So, this power station, the first electric power station, which was the DC, it was consisting of DC generators, then it was using cables, fuses were used for the overcurrent protection, and it was providing the load, and this load was nothing but it was simple incandescent lamps were there, the simple bulb loads were there, and it was feeding to only 59 customers in the radius of 1.5 kilometers. So, it was a small system, but it was a complete in the sense, and it is said the power system, because a power system should comprise of generation, transmission, as well as the distribution. So, it was consisting all. So, that is why it is called, it is a first electric power system. It was the DC system, because the DC generators were used, and at that time AC power was not even though invented. So, the DC system was there. In 1884, the motors were developed by the Frank Sprague, and with the addition of these motors in the DC system, make the electricity more and more usable, and people were more and more preferring this electricity, because now for using the electricity only for the lighting purpose is not very much appreciated, but the using the load, the motors load, and these motors loads, the mechanical loads, you can just connect it, means you can achieve various applications in normal human life, you can say. So, the motors were added in the system, but in 1886 the limitation of the DC system becomes apparent with the two aspects, that one is the voltage drop and high power loss. To minimize this, we require some transformation of the voltage, which was not possible by the DC system. So, people were starting thinking for the new one. At the same time, the transformers and the AC distribution system of 150 lamps developed by the William and Stanley for the Westinghouse was developed at the same in 1886 nearby. So, the limitations of the DC was arising, and now the AC and DC system started arguing to each other, because the DC system was educated by the Thomas Alva Edison, and AC system was educated by the Westinghouse, because this Westinghouse purchased all the patents of the AC. We will see the later on. So, the first AC, this is the first AC transmission system, was basically commissioned and operated between the Willamette Fall and the Portland, Oregon. This was the single phase. Even at that time the three phase AC was not invented, and it was having the 4 kilovolt, and it was feeding the power over 21 kilometer. So, it was a bigger, because AC system, DC system was not feasible, because this much distance if you are going, then you are incurring more loss and high voltage drop. So, in 1889 the first AC transmission system was operated. Before that, even though Tesla, this Nikola Tesla developed so many polyphase AC systems. Basically, he had the patents of generators, AC generators, motors, transformers, transmission lines, etc., and all these patents were basically purchased by the Westinghouse. So, the Westinghouse now started developing the AC system, AC power system I can say, and the Thomas Alva Edison always educated for the DC system. So, the parallelly AC and DC systems were existing for the different pockets of the all over the world, and the fight started that whether we should go for the AC system or the DC system, and due to the limitation of the DC system, the AC won the race, and DC system slowly and slowly phased out. So, that is here already in 1890s it is said the controversy whether the industry should standardize AC or DC. Edison, who educated DC, was favoring the DC. However, the Westinghouse, who had a lot of patents of AC system, educated for the AC systems. So, AC basically becomes more and more feasible, because it was possible to increase the voltage by the transformer actions, and also it is a simpler in terms of generation and the motors, and it is a rugged and very versatile, and then it was the DC system was slowly and slowly dismantled, and the AC systems becomes very, very popular. First three phase power system that was operated here in 1893, and the voltage was 2.3 kilovolt. It was in California. It was basically chosen for the Niagara Fall, which is 30 kilometers away from this Niagara Fall. AC systems becomes very, very popular, but the voltage at the beginning was very less due to the various problems in the design and availability of the insulating materials. Due to the various advancement in the insulating materials, the voltages you can see now is the various voltages keep on increasing. It was 1992 it was 165 kV, in 1923 it went to 220 kV, in 1935 it was 287 kV, and in 1953 it is 330, and so on. In 1990s we went up to 1100 kilovolts, the transmission level. Similarly, there were also improvements, or you can say new developments in the generation side. So, we also increased our generating voltage up to 33 kV. So it was and also in terms of megawatt more and more power generation for the single units. So the standards basically adapted the EHV system when it is more than 300, then it went to EHV system extra high voltage, and it is less than 300, then it becomes the high voltage, that is the various voltage level. Now these voltage levels were the different for the different countries, and each countries are having the different sets of the various voltages, because they have to use the transformers. So it is not that we can have the n number of the transformations and the transformers. So all the countries, they standardize the various voltage levels to have the interconnections, because the interconnections also had a lot of advantages when we keep on growing the AC system, AC system, sorry, and then we keep on interconnecting them to make better and better reliability, and also to decrease the cost, and so many other advantages, as you know, the interconnections advantages. And to have the interconnections, we know we require the single frequency of the system. In the beginning, it was witnessed that the various frequencies were existing all over the world, and now due to the interconnection problem, it was realized that there should be the single frequencies, and then the two frequencies after that were standardized, like the 60 Hz came to the US and the Canadian countries, and the 50 Hz came to the Europe and the Asian countries. So we are operating our system at the 60 Hz, and they are operating the system at the 60 Hz. Now here if you will see the HVDC transmission system, because I just explained how the HVAC system, how it is grown to 1100 kV. No doubt the beginning the DC was there, then there was a limitations of the DC was experienced, then AC people started thinking of the AC power system. But at the same time, this people will also started thinking if anyhow we can increase the voltage so that we can have the minimum loss and also the minimum drop. So people started thinking and developing the various system. So the HVDC transmission system was designed by the French engineer, that is the Rene theory, here when the AC system was in their infancy, because the AC system was also developing slowly and slowly. So between 1880 and 1911, at least 11 theory system, because the theory system was given based on his name Rene theory, was installed in Europe, and the prominent was the Mountier to Lens in the France in 1906. It was 180 kilometers and having 4.5 underground cables. It was only carrying 4.3 megawatt power, but the voltage level was 57.6 kilovolt and the current was 625 ampere. The main features of theory system was that it was having the DC generator, and this is a series DC generators, and it was operating at the constant current control mode, because the current control here, the current in this DC system here, the current was fixed. However, we will see in the AC system the voltage is fixed and the current is changing depending on the load. But in this DC system, he preferred the current should be constant and the voltage can be changed to control the power and the feed the power. But in here 1938, all the theory systems were dismantled, because there were several problems in this system, because the safety problems was one concern, and also there was another problems here, that we are adding the more and more series generators. There was maintenance, the cost, other problems were experienced, and at the same time the AC development was there, and it was felt that AC system is the better than the DC system. Even though it was also witnessed that in 1920 the transverters, it is a similar type of mechanical converters were developed, and it was using the polyphase transformer commutated by the synchronously rotating bus gear, but it was not used commercially, it was only used for the experimental and other purpose. So once the theory died, basically, then whole the theory system was vanished, and the people started talking about only the AC system. So till 1950, when the mercury arc valves were developed and designed, then before that we were having only the AC systems. With the development of mercury arc valves, it was possible to convert the AC to DC. So in 1954, the first HVDC, it is not DC, it is a high voltage DC transmission between the Sweden and the Gotland island of the Sweden itself, was connected by the cable. It was a 70 km, approximately 70 kilometers away, and the AC cables were not so feasible. So it was decided to go for the HVDC transmission in terms of cable in the sea, and mercury arc valves were used. So this was the beginning of again starting to think of HVDC system. Now the question again arises, why people started to think for the HVDC system? Because there were so many limitations of HVAC systems. So we'll see in the next slides. So in AC systems here, before this end this, I'll discuss this, what is the problem in HVDC and AC systems in detail. Basically in this AC system, the major problem in the AC system is that we don't have the power control. So I can say the stability problem. Stability is the one concern if you are going for more and more power transfer. So this is a stability issue. Another is your reactive power requirement. Then third is your the Ferranti effect. Ferranti effect also it will be discussed. The Ferranti effect is nothing but your receiving end voltage sometimes become higher than your sending end voltage, especially due to the charging or the capacitance between the line to ground and the line to line. And fourth, that we don't have the power control facility, power control. So the power control is not possible here. So this is one of the big problem in the AC system. So in a whole your AC system, if this is your control is not possible, because nowadays we are also thinking to provide the AC control. If the AC control is possible, then we can operate our power system in a much better and in the efficient manner. So these four are the major reasons for people are started thinking to go for the DC transmission system. These are the basically problem which I am discussing in terms of the HVAC transmission system. So to avoid these, the DC transmissions were there, because the reactive power, you can see the first HVDC transmission system which came in the Sweden and the Gotland Island, it was basically due to the charging, because the 70 kilometers cable, it was at that time it was not feasible, 70 kilometer. So then it was realized that we can go for the DC cables, and this DC cables were feasible. So then what they did here, this system, the Sweden, and this was your island, and they connected by the DC system here, and they operated, and this was your cable. So this first HVDC basically was developed to reduce the charging effect of the system. So here in this you can also see that I have summarized the 5 major problems, limitations of HVAC transmission system, that is the reactive power loss, the stability concern, the current carrying capacity, that is the charging, skid and the Ferranti effect, and the power flow control, which is not possible in the AC system. Reactive power loss, we know it very well, because the reactive power loss can be defined, that is the Q loss. Real power loss is very well, that is I square R here, whatever the resistance, and that is flowing in this your line. It is having resistance, means not only line, in the transformer as well. So in all apparatus, if you are having the resistance R and current is this, so I square R loss, that is basically in watt. It is your real power loss. Reactive power loss, basically some people talk about here I square into X. X is the reactance of that element, but it is not only this loss, because we are having another component, that is I can say XL. It is the reactive component, that is the inductive part, and we are also having some charging part. So that is basically I can say V square over XC here, that is the capacity part. So the reactive power loss is basically total of that is reactive power consumed in the element, and some of the elements they generate the reactive power. So the total sum of this is treated as the reactive power loss. And this concept is only happening in HVAC, because this X component that is here is only is occurring in AC. In the DC only the resistance is there. So this reactive power loss has no impact, because it's not existing at all in the HVDC transmission system. So this this Q loss doesn't arise, and thereby what happens, if a line which is carrying the current of both active and reactive components, so here you can see if there is no reactive component, the line can carry more active power, and then we can improve the performance of the system. Stability is one of the concern. To explain the simple way of the stability here, you know this P angle, this curve here, this is a delta, this is a power that is flowing between the two nodes of the element. So here this is the maximum power that at the delta pi by 2, the maximum power that can be transmitted through that element, but we never go for this, always we go for the lesser one due to the various regions. If there is some disturbance, then we can go in the unstable region. This is unstable area and this is your stable. So we have to operate our system in such a way that the power flow in that line should be less than, here this is a P max and here this is 0 in between. So normally we operate our element that angle difference between the two adjacent nodes should not exceed more than 20 to 30 degree, so that whenever there is any disturbance, we can go here and our system can not lose the synchronous. So the stability concern here, basically this expression is the P is derived your V1 V2 by x sine delta here, and this is basically the two elements. This is your delta if this is angle 0 here, I can say V2 here V1, and this is your x of the line. So the power flow can be simplified way. If we are assuming this line is lossless, we can just get this power flow, and we will see here we can go for the minimum delta. So this stability concern again doesn't arise in the DC system because the delta doesn't arise, only we talk about the voltage and the resistance. So no x, nothing. So this concept doesn't arise in the your DC system. Another is current carrying capability here, because the current carrying capability is basically the, if any wire or cable here which is there, the current is I is flowing inside this, here this is called the current carrying capability. Now this current is, if it is a AC system, it is having two components. One is it is a active and another is your reactive components are there. So now it is the total current which is flowing. But if your here element is having more charging, so what happens, it is a more, let us suppose capacitive here elements are there like cable. So even though you are not taking here any active power here, there is a possibility the current which is drawn here, it will be the rated of this cable, because due to this current which is flowing here in the charging. So the current carrying capability of the AC elements or transmission line or your cables are very less compared to your DC, because there is no reactive component of current flowing over the cable or the transmission line. So that's why here, as I mentioned, if you are going for the cable longer than 50 kilometers is very costly, and earlier it was not possible, now it is possible, and it is not very much feasible, that it is better to go for the DC system. Another here, that is your skin effect. Skin effect is nothing but, if it is AC system, here the current, this is your complete conductor area, current will try to go from outer side due to the, again the frequency of the system is more frequency, current will go more outer side. So here the current is non-uniform, because the in between at center the current will be less, outside it will be more. So what happens, the density of the current in this over this area of the conductor is different, and that's why the resistance, effective resistance will be more, and thereby the loss will be more. So this skin effect only arises in your AC cable, AC lines, because AC has some frequency f, and that's why it is happening. If f is 0, it is a DC, and finally it will be, the current will be the uniform, and therefore that's why always we say RAC is always greater than your RDC. Means the resistance, if you measure the AC resistance, will be more than your the DC resistance due to your skin and the plasma effects. If another conductor is there, again there will be flux linkage. The Ferranti effect, which is basically if this two system here, the big transmission line is there, and this is called V sending end voltage, and this is your receiving end voltage. At the lightly loaded or no load condition, your the Vs magnitude here I am talking, it is less than, sometimes it is your VR. And this is called Ferranti effect, and this is due to the charging, basically charging of the capacitive form due to this conductor with the respect to ground. So what we do, we go for the various mechanism to limit this voltage, especially if you are charging the line, there is no load, and then the high voltage will be there at this end, and there will be again the tripping of the system. So we put the various here the reactors, we put the line reactors if the line is very long, and then if still you require more reactive powers, then you can put the bus reactor, and sometimes also we use the tertiary reactors as well. The another major concern here, the power flow control is not possible. Power flow control, I mean that we want the power flow control in the smooth manner. Sometimes we also want the power should be reversed from one direction to another direction, which is not feasible, not possible in the AC system, unless until you are putting another device. Nowadays, again, the flexible AC transmission systems are invented. They are in the place in the system. Now, with help of them, we can control the power in the AC system as well. But at that time, earlier it was not possible. Before 90, it was not possible, and HVDC control was only possible. So that's why the various types of links were developed, and based on those links, we were controlling the power flow as well in the lines as well as very neighboring areas. So to avoid these 5 limitations, it was found that HVDC is better in terms of several problems of the HVAC transmission. First, you will see regarding the reactive power loss. Here you can say there is no reactive power loss at all, as I explained, is true. The stability concern, you can say there is no stability concern in HVDC system. No doubt it does not mean that we can flow up as much as power in any transmission line, HVDC transmission line. It has some limit, but that limit now is your thermal limit. However, in the AC system, we are having thermal limit and stability limits and the voltage regulation limits as well. But it depending on the length of line, which limit is coming first is basically decided by the length of line. If length is very long, your stability limit is the governing criteria than the thermal limit, because thermal limit value is very high. If line is less, then stability concern is not there, very less, so the thermal limit will be governing criteria. But here in HVDC, only the thermal limit is the governing condition. You can load your transmission line up to the thermal limit where it is designed. But the stability problem is not a concern of HVDC transmission. No charging current, because if there is no change, is smooth here, the perfect DC voltage and perfect current is flowing, so there is no charging here, and there is no capacitive. The charging current is not there, because once the capacitance will be formed, once you are having the two potential difference, medium is the dielectric medium, air is also a dielectric medium. So capacitance are formed, but it is the constant and thus no charging. Here no skin effect, no Ferranti effect, because the charging is not there. Skin effect is not there because again the frequency is 0 here in the DC system, and the power flow control is possible, that we can control our converters in such a way that we can control the power, because the DC power here, it is a PDC is your VDC into your IDC, means the DC current multiplied by the simple DC current, and this is called your PDC. However, your PAC is the voltage, AC voltage, and your AC current into the cosine theta, then theta, or here I am writing theta is the power factor angle between the voltage and current, and the cosine of this, it is a power factor. Here the PDC can be controlled by the voltage control, can be controlled by current control, or can be controlled by both, but we prefer the current should be the constant and the voltage can be varied, and thereby we can vary here the DC power. So here basically what the DC power is very effectively controlled, even though it is not only controlling from 0 to its maximum value, it is also possible that we can control its the minimum value in the negative direction, means because the voltage can be vary from minus V to 0 to plus V, so that we can have the power reversal also with help of this HVDC link, and that means you can have a full 2 quadrant operation, because the 2 quadrant which I mean here, this is your ID, we are, as I said, ID is a constant, and your voltage here, the positive voltage here, negative voltage, you can operate this and this coordinate very effectively, and then you can basically control the power from one end to another end, and then as well as you can return it back. So the controllability here is very, very better and very effective. But some other advantages, minor advantages are also there with your HVDC transmission system, that it is said that it requires less space compared to the AC system for the same voltage rating and the size. Because the same voltage here, if you are having, let's suppose 400 kV system, 400 kV system means you have to design this 400 kV is your RMS value. So you have to design your system for its peak value, and peak value here is nothing but multiplied by under root 2. So, you are going to multiply this, your design is basically, but in the power here calculation is a 400. So, what happens, you require the less space in terms of, suppose you are having the insulators, if you are the cross arms, and also in the substations clearance here and there, we require the less space in the DC due to this factor as well, because we always see the peak voltages for the AC system. Another advantage here, that the ground can be used as a return path. As we will discuss in the next and other lectures, that the various type of links are feasible. It is called monopolar, bipolar and homopolar. In the monopolar, only one pole, one wire is there, and the ground is used as a return path. So, we can use the ground as a return path, means we can minimize, we can reduce the cost of the conductor. But it is not very practiced, because if you are using ground current, then there are so many other problems like the communication interference, there will be some erosion, there may be some, if there is some potential is developed, and some there is shock and safety measures as well. So, ground is used as a return path, especially in the emergency conditions when there is one problem in the one pole. So, then we can use the ground as a path for providing the power for the limited period of time. Especially in the bipolar, if one pole has gone, then we can use the another pole as the monopolar operation, and we can operate, we can give the 50% power transfer from one area to another area. So, this is another advantage, that it is possible if AC system fails, you have to completely shut down and then you have to maintain it. Another advantage is the less corona loss, because the corona loss, it is always this proportional to F plus 25. Here there is I can say PC corona loss is proportional to this. In DC F is 0 and your AC is here F is 50 or 60 hertz. So, it is the more loss in AC system compared to your DC system. So, what happens here, the corona loss in HVDC system is less compared to your DC system. Another is the radio interference. Here the RI, if frequency is 0, so radio interference is 0, but due to some harmonics and other thing, there may be some radio interference, but this value is very, very less. So, overall we can see here that the advantage of HVDC is basically taking place, and it is trying to minimize the limitations of HVAC transmission system, but it is not, HVDC is not having limitations. It is also having the various limitations in terms of its cost, in terms of generating harmonics, in terms of tapping up the power, and in terms of some other limitations like here you can say the overload capability, the blocking of the reactive power, and several other things there. So, advantages here, some other various minor advantages are listed here. You can say the fault clearing time, the compensation problem, no compensation is required for the capacitance, low short circuit, no transmission of short circuit power, it has a less and no switching transients, asynchronous operation is possible, and it is cheaper for the long distance problem. So, all these again we will discuss in the next lecture, but in this lectures my main intention is to give you a concept why this HVDC transmission system is taking place all over the world, especially for the long distance transmission. In those countries which is very, very small in the geographical area, HVDC is not very feasible for the long distance transmission. So, we are having basically the three types of HVDC links for the control of AC/DC power system. One is called your, if you want to have a bulk power transmission, and second is it is called back to back concept, back to back modulation of AC network. Basically, here in the bulk power transmission, what I want to say, if you want to transmit the power from one region over a long region without tapping power in between, it is called bulk power transmission. Here the concept that the generation, if suppose in this area is very high, load demand in this area is very high, we want to transmit power without tapping in between, the DC is the best and the cheap option. But that's, as I was mentioning, if area is small, then it is possible that you can go for the AC system and then you can transmit the power. But those countries is very long and you want to transfer over the long distance, there is no other options, you have to go for the DC system at all. So we have to use the HVDC bulk power transmission, especially in India. It is very important. If you are trying to trap power from northeast and taking it to the central part of the India, we require huge HVDC links to transmit the power. But this concept is now common not only here as the basic of here to control the power. Here the concept was to transmit the power. Here this control aspect, even though if you are having the two regions very nearby, here you can have your the DC here back to back, even those converter and inverter stations are put together very near to each other, maybe less than 1 kilometer or so, even though in one substation. And the purpose here that we can monitor how much power is flowing from one region to another region. So that's it's called back to back, because here inverter and converter is same back to back. Here only we don't want to transfer bulk amount of power. Here we want to control the power, because it is based on the contract, it is based on some negotiation, and also in terms some sort of the emergency. You know, if there is some problem in this region, this link is there, then we can open this and the disturbance cannot be propagated in the another region. But if you are having an AC line here, certainly the disturbance here that can go there. If it is not protected well, then both system will be the collapse. So it has various advantages. Here we want to control, we want to provide the emergency support, and also we can just meet the contractual requirement. So the back-to-back connections are there. Here the modulation of AC-DC system basically is meaning that if you are having some here AC line and this line is very weak, sometimes there is some problem here due to the power oscillations, or you can say power swings are there, we can have another here HVDC link, a small HVDC link that can support this one. Means whenever there is a problem, we can just control in such a way that we can modulate the power over this AC line. Means it is used to improve the stability of the system. So you can see the three objectives are for the HVDC transmission system. Here it is basically to feed the power over the long distance, means large power over the long distance. This is the, here also control, we do it control, no doubt, but the basic is we huge power which is fed from one area to another area. Here, as I said, this one is the control of power, is the primary objective. Thus we can control the power, how much it is going. If it is AC system is there, so if this area is drawing more power, it will be flowing here without any control, you cannot control here. But the DC here connection is there, you can fix the power, it cannot take more power from this area unless until this here controllers are tuned for this one. This one is basically used for your stability of the system. So it basically it is used in this AC system to stabilize the AC-DC system as well. So that's why here the transmission part is now going, if your objectives are these, then you have to go for your DC systems, and it is, we are talking about the high voltage DC system. So nowadays that's why you are having the AC generation, we are having the AC distribution system, and of course the utilization now we are again shifting from the AC to the DC, because we are having a lot of power electronics based devices, those are giving, and also communication, mobiles and other, the DC power are required in the houses, but the transmission distribution is AC, and after that again people are using some conversion technology to get the DC power for the charging of the batteries here and there. Generation is still your conventional generators, they are AC. We are also generating some part of the DC power based on your photovoltaic. But if you want to connect in the system, then you should require some converter, and then you convert to the AC system, and then you can connect it to the grid. But the transmission, this transmission is the combination of your AC and DC system, especially based on the various objective. So it is believed that your transmission part will be the mixture of your AC as well as the DC system, and here the DC system we are talking high voltage DC. We don't have the DC low voltage DC, because again the problem of high loss and the voltage drop will be there. So high voltage DC transmission DC transmission. Along with your AC transmission, it includes both your high voltage EHV and the low voltage AC transmission as well. So, this is the scenario which is emerging all over the world. So, to conclude in this whole lecture number 1, basically I discussed the course contents, which will be giving the basis that what we are going to discuss in the various modules, various lectures, and it was decided and based on that. So, the total this whole course will be basically scheduled for 35 to 40 lectures based on the various contents, and also some numerical problems will be solved and will be showed so that the students can get benefited, even the teachers also they can be benefited from this. And here in the first lecture I just summarized the evolution of the power system, along with the especially emphasis was your DC system, from your small high voltage DC systems, then we went for the large DC system, and then we discussed some of the limitations of HVAC system, and then along with we discuss that how this DC system will be the advantageous to remove the limitations of HVAC system. So, the various disadvantages are also there, that will be discussed in the next lecture, and also we will discuss the various type of links in this module, and also the various of component. The basic background will be given in this module, so that we can move to the various modules. Then it will be analysis, control, the protection, then analysis, and then we will see the total performance of HVDC, DC and the AC system as well. So, with this I should stop this. Thank you.